Good, thank you. Well, thank you so much. It is a great joy and rather an honor to be speaking at an object-oriented. It's not object-oriented anymore, is it? Programming Languages Conference. So thank you so much for inviting me. One of the really nice things about working in a lab like Microsoft is you get to work with a lot of other smart people and encouraged to study things other than your core speciality. So this talk is about something I know very little about. You should, you should regard it as a kind of Simon's tutorial for what a programming language person wandering into a deep lake filled with very smart people has found out by paddling on the shore. So I'm hoping that for every person in the audience who knows a lot about AD, there will be sort of 6 who don't know very much, have heard of it, and kind of wish they know a bit more. It's the 6 that I'm really addressing here. So you can regard this. And so let's see, we will finish in an hour, but please, if you'd like to ask questions on, as we go along, please do ask. I'll repeat the question back. We don't need a microphone. I'd just like to feel that there was some kind of dialogue going on. But I got plenty to say. So here's the picture. It's kind of a little tutorial of why should we be interested in AD. So this is what all machine learning programs do. They recognize cats. And so there's some kind of neural network, whatever that is, who knows, but it's a function, right? It has some inputs and an output, and the inputs are, the inputs are these, the cat pixels, and rather a lot of weights, right? These are the, floating point numbers, a lot of them, 100 million of them, and one output that says how cat-like it is. And our goal then is to try to figure out, our goal is to try to figure out what weights would make it output the right, yes for cats and no for dinosaurs, all right? That's our plan, and how we're going to do it. So the way you typically do it is using gradient descent. So now I've shifted my picture to be a function with just a lot of inputs. It was like that before, really. It had a lot of pixels and a lot of weights. I've just glommed them all together now. On the left, some inputs and a real numbered output, and that real number is meant to say how cat-like the picture is. And our goal is to try to find the inputs that sort of minimize the output. That's roughly what. So we're going to try to use gradient descent to do that. So what does that mean? We're going to, if we know what f is, and we do, that's the neural network, then, and if we could figure out the direction of greater slope, I mean, f defines some kind of surface in a very high dimensional space. If we could figure out the direction of greater slope that would take us down, we're trying to minimize it, we could go down in that direction. That's the idea. So all we do is we figure out the slope, and then that's delta p, right? That's this guy here, and then we adjust the weights by alpha. Alpha is the learning rate, and you may wonder how big should alpha be? Well, nobody knows, but you sort of suck it and see. But at least you go in the right direction, and then hopefully you keep going down until the slope gets to be close to 0, and then you're near the bottom. That's the idea. Okay, so in order to do this, we have to be able to find the direction of maximum slope. So what is that? Well, let's see. We want to, if we knew the derivative of f with respect, let's say it's just got 2 inputs, r squared, x and y. If we knew how sensitive f was to x, that's written here, df by dx, here. If we knew that number, that's the sensitivity of f to x. And the sensitivity of f to y, well, those 2 form a little vector that is the direction of maximum slope, right? Because if it's very sensitive to x, that will be big. So it will be big in x and little in y, and that's going to, so we're just going to move down in that direction. It make intuitive sense? That's what we want to know. Differentiate f with respect to these 2 things. And just keep repeating. Okay, so now we want to differentiate this rather complicated function, but it is just a function. It's all functional programming with respect to these 10 to the 8 inputs. So there are 2 main ways people go about this. One is sort of runtime methods that usually by some kind of operator overloading, you really run the original function, but instead of manipulating floating point numbers, you manipulate sort of a floating point number and its derivative or something like that, and then you and then from this instrumented version, you can sort of recover something about derivatives. That works very well for forward derivatives. You have to do what the Tapenade paper calls acrobacy to do reverse derivatives. A nice English term invented by French people. But we're going to talk about compile time methods in which you take the code for f And we're going to transform it to code for something that will compute the partial derivatives of f. Does that make sense? So it's just a source-to-source transformer. There are quite a lot of AD things that work like that, and that's where we're going to focus. And moreover, we're going to focus on ones not just with the cat picture one needed r to the n, where r is very big, to r, just a single floating point number, but we might also take r to the n to r to the n, or r to the n to r to the m, right, possibly different. Right, so n and m might both be big, and we'll deal with that as well. Yes, please do. Yeah.
You said F was a neural network. So
yes.
Do we have the code for it?
Yes, we do have the code. Yes. And in fact, moreover, the code is usually in this room when we're talking about looking at programs and analyzing, we're talking about programs that are 10,000 lines upwards. The code for these little f things is typically 30 lines or 300 lines. It's quite little code. It just has a hell of a lot of data. Those floating point numbers, the weights input. That's the magic of the actual code is quite small. Yes, we do have the code. Oh, then there's all sorts of, so there's a lot of beard tugging in the machine learning community about, learning rates and false minima and, is it differentiable everywhere? And mostly, and so I'm going to sweep all of that away. I'm just going to ignore all of those problems, right? They are problems, but the strange thing is, the magic of machine learning is it works unreasonably well. That is, if you ignore all the problems, it still works. It's really quite annoying. I mean, there are whole books about machine learning that talk about this stuff, and there's a lot of suck it and see, a lot of clever ideas, but there's a lot of trial and error actually. But it's a good question, but I'm not going to tackle it today. We're just going to do differentiation. Okay? Yeah. Anybody else? Yeah. All right. Let's see. Where have we got to? Yes. Compile time methods. Yes. And this thing. I want to tell you a term you can impress your friends with at parties. If you've got a function from r to the n to r to the m, the set of partial derivatives is actually not just a vector, it's a whole matrix, and this is called the full Jacobian. Right, so it's an impressive term. Okay, so now, the AD literature, because this is a practical problem, the AD literature is dominated with a lot of practical papers. There are some very smart people that I'm still trying to figure out who've written well-written papers and have truly remarkable implementations. But when I have tried to read these papers, as it were, with a programming languages perspective, I found them to be quite, strongly example-led. I love examples, but I hope to see something completely systematic towards the end. And typically, I find an implementation towards the end. And also, there's a lot of language about operational stateful language, state machines and graphs and perturbation confusion and counters. So all of this is good because it works, right? They build things that work, but I found it quite difficult to understand. Then I sort of read this paper by Conal Elliott. So really, mostly this talk is a sort of Simon's interpretation of the genius of Conal. Conal is a functional programmer who's deeply principled. He thinks for a long time and writes very carefully. And so if he writes a paper, you want to pay attention to it. It will be worth your reading. But you do have to cope with co-Cartesian categories. And continuation passing style, and all sorts of other things like that. And even after the benefit of a personal tutorial with Conal, I still find it tough going. So you should regard this talk as a sort of exploration of some of the foothills of this paper. I'm getting on to the sort of next bit later, but I'm not even going to cover the whole of Conal's paper. But he takes a very PL perspective as well. Okay, so let's get to the meat of it. What exactly is differentiation anyway? So this is... first thing to do is to say, usually when you do differentiation at school, it's from a number to a number, reals to reals, right? When you get to university, you deal with r to the n to r, but when you get to a PhD, you get r to the m to r to the m, right? So but we want to do more than that, right? We'd like to have functions that can take pairs, or a pair of arrays, or an array of pairs, or more structured type, maybe even lists. So we like to have a richer collection of types as the input and output values for our functions, right? Because we're writing programs here. Let's see, and these are actually realistic in practice. And this also means, incidentally, that we're only going to consider functions of one argument here, because if we have many, we're just going to tuple them up. Nothing is going to be higher order in this talk yet. I don't really know how to do higher orderness yet, though I think we're getting close. Conal is certainly quite close. Now, so that's a sort of, all our functions go from S to T, but S and T are going to be rich types, not necessarily just floating point numbers, is what the message for that last slide. Next bit, what is differentiation? Well, if I take the derivative of a function from S to T, I'm going to say that I get back df, or del f, or I'll call it df in this talk, is the derivative of f, and it's going to take a value of the input domain, here of type S, and return what? A particular kind of function from S to T. So here I'm using this lollipop, this linear arrow, not in the sense of the talk earlier today about linear types. Forget that. This is a different use of linear, but I'm going to use the same symbol and indeed the same word. Sorry about that. Linearity is so important, it just pops up in maths in lots of different ways. So, so a linear map from S to T is a particular kind of function. So what kind of function is it? The idea is that df at point P, df applied to P, is a function that closely approximates the shape of f near P, right? So, by closely approximate, what I mean is that f of P plus a little delta P, you know, a little nearby P difference, is going to be, well, what? It's going to be f of P here, plus, and now here's this funny function. Remember, df of P, up here, is going to be a linear function that applied to that little delta function gives me a little delta in the output. Does that make sense? All right, so that's what a derivative is. Yes, Sophia? Do we assume that S has got the operator plus? Excellent point. I'm going to come back to it in about 5 minutes. Yes. But we do, yes. Yes. In fact, everything's going to be a vector space. Good observation. Okay? So, let's see. Just notice, I say, df doesn't really approximate f itself, right? It doesn't behave like f. It behaves like the sort of the deltas on f near P. Okay? Now, a little bit more about what I mean by, so I'm going to call these lollipop things linear maps, and they're particular kinds of functions. Right, so to take a particular example, if you have a function from r squared to r, you could think of that as being like a curvy surface, right? The height is the result of the function. The x and the y on the floor are the inputs to the function. It's like a curvy surface. And then linear maps in this world would be planes rather than curvy surfaces, okay? So that's an intuitive idea of what I mean by linear. So that's what I mean by, so then one of these linear maps would be like a tangent to the curvy surface. That would be a derivative of the curvy surface, would be a plane that is tangential, right? I want to characterize this a little bit more precisely in a second, but I just want you to get the intuition. Mostly, though, we're going to think of abstract data types, of linear maps as an abstract data type. So it is a kind of function, but I'm going to think of it as something that I build up with a set of operations. So I'm going to think of it as a different type to ordinary arrow. You can think of it as a subset of ordinary arrow, but I'm going to regard it as an abstract data type. So that means that when I write this approximate thing, I can't say dfp applied to delta p, but what does apply to mean? I need an apply operator, don't I, right? Because I've got, in my left hand, I've got a value of type s lollipop t, and in my right hand I've got an s and I want a t. So I need an apply operator, and that's what this funny dot, right? I sometimes call it funny apply, right? So a funny apply takes a linear map and an argument and applies the linear map to the argument. So here's a sort of summary. There's its type at the top. So you can think of it as being the apply operator, but you can also think of it as a way of taking one of these linear map functions and turning it into an ordinary function. Does that make sense? Look at its type. S lollipop t, arrow, S arrow t. Make sense? Right? So it just takes it out of the lollipop space into the ordinary space, presumably a subset of the ordinary space. And you can also regard it as a way of giving the semantics of a linear map. If I say, here is a linear map, how do you know, what is its semantics? Its semantics is just the function that it behaves like, right? And that's what lollipop tells you, okay? So far, so good? All right, linear maps. So that's linear maps. Now, so the first thing when I was reading this paper, it's all very well saying this about linear maps and talking about curvy surfaces and planes, but what is it about a function that makes it linear? And it could say, oh, it's just a matrix, right? That's what AD kind of people, they just think matrix, Simon. But I don't want to think that, because matrices means I'm just dealing with r to the n cross r to the n. I'd like to say, for any s and t, what is it that makes a function from s to t a linear function. And here it is. I mean, this is standard stuff. I've not invented this. A function from S to T is linear if, when you apply it to the sum of two things, you can apply it individually and add the results, get the same answer, and you can also scale it, right? So here's k times the n. You can multiply by k before applying the map. Does that make sense? These two things define what we mean by linearity. And you can see, I think, the way that commuting with plus and scaling are what you expect with linear functions generally. So but it's a nice way to characterize it that isn't specific to the particular S and T. But, as Sophia so acutely observed, of course, we have to worry about what these plus and times things are, right? Because they don't exist on every function, every type. So we just have to work over vector spaces. In fact, vector spaces, we're going to need vector spaces with dot product. Okay, so what is a vector space? It means we have an addition operator over the vector space. We have a scalar multiplication. Note, this is not v to v to v. This is real number to v to v. It's scaling by a real number. So it's an asymmetrical. This multiplication is an asymmetrical multiplication by a real number, a 0, and then there's a dot product as well that takes two v things. And in the word of vectors, it just multiplies corresponding elements and adds them up. It's just the dot product of vectors. But for something to be a vector space with dot product, it has to have an operation with this signature. And then, of course, these operations need to obey the usual laws of associativity and distributivity, and 0 cancels everything. You can imagine all the usual laws. I'm not going to write them down. Many of them were in the talk earlier today about semi-rings. Dear me. From Amir, yes. Yes. Yes, Amir, over there. Yes, question.
Is there any abstraction regarding the scalar?
Oh, yes, so this scalar doesn't really have to be a real number. It can be any field, yes. But I'm going to stick to real numbers for today. So it's very helpful to be able to abstract over lots of different vector spaces. It's not so useful to have lots of different fields in practice, but absolutely you can. Everything generalizes to fields. Yeah, thank you. Okay. So that's what we're going to need vector spaces. And if you're somebody who knows what a tangent space is, it's really the tangent spaces that need to be vector spaces, not the original S and T. But I'm going to sweep that under the carpet for the purpose of the talk, because there's too much else to say. Okay. All right. Okay, so let's see. So, of course, some things we know, and we were talking about matrices, and everyone says, matrices describe linear maps, and indeed they do. So, matrices and linear maps really are closely related. That's because R to the n is a vector space, and a function, a linear map from R to the n to R to the m, is isomorphic to, in one-to-one correspondence with, matrices, n by n matrices, in fact. And then the funny apply operator just turns into matrix vector multiplication. Does that make sense? And so I think the thing that Conal showed me is that if you look at most of the AD literature, it's very imbued with matrices and vectors. And what Conal showed me is we shouldn't think of that. We should think of linear maps in this more abstract way, with vectors and matrices as being a sort of particular instantiation. Okay, that's very insightful, I think. Okay? All right, now, where we're going to go. Right, so, yes. So, why do we not want to just think of them as vectors and matrices? One reason, apart from just being a bit more abstract, is that it allows us to have S and T that are richer than just R to the n, right? We can have richer input and output types if we're not fixated on matrices. Right. Okay. So, let's see. Next piece. Once we got to this idea of linear maps, now we can look at what happens when we differentiate functions. So, if I have a function f that's simply the composition of g and h, which I might write here as, let's see, f of x is g of h of x, or f is g composed with h, how would I differentiate that? Well, the picture at the top is helpful. The input comes in, it goes through h, and then it goes through g, right? So remember, the derivative of f is a little linear map that if you give it a little wiggle on the input, it tells you how much you waggle on the output, okay? So if I wiggle a little bit on the input of h, and I have dh, then I can get a little bit of waggle on the output of the dh up here. I get a little bit of waggle there, and I put that bit of waggle through dg, and that tells me how much waggle I get on the output. Does that make sense? So if I wanted df down here, come back, yes? df down here, I wanted this guy, df, well, what have I got to do? I've got to compose the linear maps. First of all, I apply dh to the input, and then I apply dg to that, right? But remember that these d things all have as their argument, remember their types? They all have as their argument the point at which, remember, they're linear maps at a particular point, right? So for h, it's fine, right? h, look, we just need to give it x, right? That's the point. But dg, the linear map from dg, well, that has to be taken at h of x, right? So I've got to give it h of x here. Right? And then this composition operator, now here, that is not composition, that's composition of the linear maps, but it has a very familiar looking type, doesn't it, right? Just ordinary old composition. But remember, these linear maps are abstract data types, so I'm going to use a special composition for it. So far, so good? This is the chain rule. You all learnt it in school. It looked more mysterious then. I'm hoping now that you think, well, how could it possibly be anything else? It just has to be like this. Okay? So, let's see. And this composition operator, I said that funny apply gives us the semantics of linear maps. So every time I introduce a new operator on linear maps, like composition, I have to give it semantics. How can I give the semantics of composition? By saying what happens when you funny apply it to something. And when you funny apply the composition to a delta p, of course you just funny apply m2 to delta p and then funny apply m1 to that. Right? So simple. That's the semantics. So this is a standard pattern. Every time we introduce a linear map, we're just going to give it semantics by saying how you funny apply it. Okay. So far, so good. So now all we got the idea of linear maps and we got the chain rule, and now we're going to go back to gradient descent. And a big underlying question will be, how are we going to represent linear maps? Remember, they can be represented by matrices, at least in the special case of r to the n and r to the m. But we don't necessarily want to represent them like that, and we're going to explore several different representations. And that's the wiggle room that regarding linear maps as a sort of first-class abstract data type in its own right gives us. So, let's just take a pause and remember what are we trying to achieve? We are trying to figure out the direction of greater slope. So we are trying to differentiate f with respect to x. This is an input. At the moment, I'm just sticking to r squared to r again. Right, the simple special case. I'm trying to differentiate f with respect to x and with respect to y. And that's the vector that I want. Now, how can I if I have the linear map, if I have df, how could I differentiate f with respect to x? How could I get the sensitivity of the output with respect to x? Well, it's kind of easy. If I just apply df at xy2, 1, 0, what does that do? That says if I make a little wiggle of one step in the x direction and no steps in the y direction, how much waggle do I get on the output? Well, that is the sensitivity of f to x, isn't it? So, this is df by dx. Right? And now I can apply it to 0, 1 here, and I get df by dy. Is that obvious now? That's the way it has to be. So, hallelujah, to do my machine learning problem, to recognize cats, all I have to do is construct this linear map and apply it to plan A then, apply it to 0, 1 and 1, 0. Well, there's 10 to the 8 inputs, so I actually have to apply it to 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 1, 0, 0, 0, 0, 0, 0, 0. And I have to do 10 to the 8 iterations of this. And what is one iteration? Well, one way to represent the linear map is by executable code for applying it. So here, I've said I'm defining f prime, which I'm going to, as it were, construct source code for, whose behavior is, its semantics is given by this. It's meant to be given a little delta x and delta y, give me the result of applying the df to delta x and delta y, right? So if I could do a source-to-source transform from f to give me f prime, now I could call this f prime 100 million times and I'd be done. Okay? So, and that works actually, it's just rather slow. Maybe you can make it fast by putting that code inside the loop and doing clever compiler optimizations to lift stuff out of loop. And Amir, the same Amir, has a talk at ICFP about exactly that. However, there seems to be something wrong about doing anything 100 million times. If there's a better way to do it, and perhaps there is. So that's one way. So here's another possibility. Maybe we could represent the linear map, instead of by executable code, that was representation number one, we could represent it by a matrix. After all, this is in fact R to the n to R. And this looks hopeful, right? Because what matrix do we get for this particular linear map? The linear map for this particular df, well, it's a 2-vector. And moreover, it's a 2-vector. Remember, since funny applying it to 1, 0, which now is just dot product, in fact, that's all that's left, because it's a 2-vector funny applied to a 2-vector, so all we got is dot product. What does this do? This picks out the first component of dfxy, and this picks out the second component. So in fact, dfxy as a 2-vector simply is the 2 partial derivatives that I wanted. That seems like magic, right? So if I just represent my linear maps as matrices, in this case just a vector, it's got all the answers right there. I don't have to do any further work. Job done. So I think, oh goodness, what's all the fuss about then if it's so easy? But it's not so easy. There is a hidden trap of stupendous proportions lying in it. Here it is. Here's why it fails. Suppose that F was G composed with H, and I'm here giving you the types of F, G, and H. So F, as advertised, takes a R to the big number to R, because those are the kind that of interest to the machine learning folk. The cat, down to the cat likeness. And H takes this R to the 1,000 to an R to the 1,000, right? And G smashes the R to the 1,000 down to R. Well, that's well typed. But now what happens? We're representing all these linear maps as matrices. What is the linear map for H? What does it look like? It's a matrix of what size? A million. 1,000 by 1,000. But actually, of course, I don't really mean 1,000. That 1,000 should be 100 million. So H's matrix would be 100 million by 100 million, which makes even today's memories creak. Right? So this is a bad idea. Right? You can't really represent linear maps as matrices. The intermediates for even rather simple programs like this go very bad on you very quickly. And all manner of special tricks to represent sparse matrices don't really work very well. Okay? So, plan B fails. So it's time for plan C. Let's see. Oh, plan D. I think I missed out plan C. I decided not to tell you about it. Plan D is to transpose the linear map. So this is the one slide that I have really found it difficult to find a good explanation for. I want an operation called reverse funny apply that takes a linear map from S to T and a T and gives you an S. Right? And you can see that, linear maps, because they're linear, this isn't going to be the inverse. This is going to correspond to the transpose of a matrix. If you regard the linear map as a matrix, then this, as it were, I want to transpose the linear map and then apply it. So reverse funny apply is going to have this type signature, and it's going to have this property. So this is the property that I find it hard to justify intuitively. I'm going to prove to you that is the property that if it has this property, then it's really useful to us. I can't quite say, where did I come up with this from? I came up with it by reading some papers and talking to clever people. But I'd love to come up with a more direct explanation. But let me read off to you what it says. It says that reverse funny apply has the property that if you take any S and T in these vector spaces, right, and you and notice also that, oh, drat, I wrote this type signature backwards. In fact, for reverse funny apply, I put the argument on the left and the linear map on the right. So this type signature here should say T arrow, S lollipop T, arrow S. Okay? Sorry about that. It's just a typo. So here it is. So this is M, reverse funny applied to T. That gives me something in S, right? And then I'm going to dot it with this value s that I'm quantifying over. And that's going to give me the same thing as if I take m and funny apply it to the s and dot that with the same t. This is a little mysterious. There's something beautiful here, because you can see that I've got T, M, and S in the same order. I've just sort of wiggled the symbols around a bit. And in fact, it turns out that because these are vector spaces and so forth, this property does uniquely define funny apply reverse. This isn't just a property that it has. This is actually a definition of it. And moreover, if you were in the special case of matrices, the reverse funny apply really is matrix transpose. So look at this equation. Right, remember that A funny apply X was just A apply A times X, matrix multiplication. Well, matrix vector multiplication, actually. So reverse funny apply is just transpose the matrix and then multiply. So it's not inverse. But I'm going to show you why this does does something very useful that we need to do. And I'm going to show you why this property is useful. But maybe somebody afterwards can educate me in why, where this property comes from, how it springs up. You'll probably say it's Phil will probably tell me it's a closed Cartesian bifunctor or something. Now, why is it useful? So, here's why it's useful. Suppose I have, remember I wanted to compute this value. This is one of the values I want. That's the partial derivative, right? That's the partial derivative of f with respect to x. That's one of the values I want. So, well, this is equal to 1 dotted with that. Why? Well, because this one is we're in the real numbered space. So actually, remember, the result type is real. We're in T space. So that dot is just multiply. So 1 times anything is the same as the thing. And now I've got something that looks like the left-hand side of the equation. Sorry, the right-hand side. T is 1, M is df, and S is 1, 0, right? So I can rewrite it to the left-hand side of the equation using the rewrite. Here it is. So I've just rearranged. Same symbols in the same order, different thing. And now I can see that all I'm doing here is I'm picking out the 1, 0 component of this thing. So it's the first component of this guy. So if the long and short of it is that if I can compute this thing here, if I can make executable code which computes this function, df, funny applied to a delta, then I will get all the components that I want in a single blow. This is the only tricky bit of the talk. You sort of have to push the symbols. You think, oh, yes. And now we're just going to see how to actually do that as a source-to-source transform. Okay, but the name of the game is going to be, we're going to start off with f. We're going to source-to-source transform it to f prime reversed, which is going to be code that does this game here, computes this thing. Okay? All right. So now we're going to do the source-to-source transform, like lots of other people do, but for a very simple language. Here is our simple language. Just remember, since we're talking about functions, functional programming is just the right thing. So we've got constants, variables, first-order function application. So as I say, pairs. That's for because we do a lot of tupling. Then we have lambdas in applications, but actually we're really only going to use lambdas in a very specific case towards the end. Because I don't know how to do the full generality. Mainly this is going to be first order. Lets are going to be very important, and we're going to deal with if as well. Okay? And our plan is going to be that we're going to take the original program, we'll do a source-to-source transform to give the full Jacobian, which is some actual source code that would compute the linear map represented, however you decide to implement the linear map. Then we're going to do a source-to-source transform that will produce the code for f prime and the code for f prime reversed with these signatures, right? These are called forward mode and reverse mode AD. And the reverse one is the one that we mostly want for the machine learning kind of application. Okay? That's our game plan. So let's actually do it. Here is, how do we do this first step, which is to make df? Remember the df, he was producing the linear map. How can I produce that linear map? I've got the code for f, and I want the code that produces the linear map for f. And here it is. This is automatic differentiation in one slide as a source-to-source transform. So what is it doing? Well, so this funny delta S thing, that's the source-to-source transform with the Oxford brackets, and we have a case for every syntactic form in the language. So the things on the left are, the syntactic forms of the original program. The things on the right are also terms in the language, but they have type linear map. In particular, here is the typing rule that if E has type T, then this transform, grad SE, is a new expression whose type is S lollipop T. That's the invariant to keep in mind, right? That grad S T, grad S of some expression E, if E has type T, is a linear map from S to T. Yeah, Sophia.
Does the dependence on S apply on the first line where you emit 0?
Yes, so here, there's a funny little thing, the funny dependency. What is this 0? I'm going to tell you what 0 is. And it is important that it goes from S to, if K was a floating point number, so then it would have to go S to float. So I need 0 to have type S to float. We'll see that. Yes. So this invariant applies throughout. And we'll look at these. So let's see. I'm going to look at these one at a time to introduce the linear maps that we need. So we need a wider variety of linear maps. So here is, in fact, I thought I'd start with an example. Always have an example first. Here is a complete definition for, here's a little function. F of x is x times x squared, which in this language looks like multiplication applied to the tuple, the pair, xx. And so there's this funny little impedance matching thing, let dx equal 1. So I had to do that up here. And then what did I do? I just routinely applied these rules. What did I have to do? I had to say, what did I have? I had times of xx. So the times, that was this rule, f, so I had to do this. Here's that composition comes from an application of this call rule here. Let's see, I think it's actually going to be better for me if I do this duplicate thing, and then I'll be able to, I won't have to keep looking backwards. Duplicate. Is this going to work? It still works. Good. Yes. So then, where do we go? So that's right. And then we had this pair thing, right? Because we got this pair XX. What happened there? Well, we have to apply this rule. And that made a little cross appear here. That's fine. And then we got to the x's, and then we used this rule, and this little dx appeared. Unfortunately, that little dx was bound by this let, which we bound at the beginning. So I hope you can see that we just cranked the handle of these rules, and we got that code, right? Just simple syntactic transformation. And by the way, this dx is just there's nothing magic there. It's just a derived name. If I've got x, it's like x prime and x double prime. It's just dx in the front. There's no magic operator there. It's just it's a name for a variable, that's all. Same with df, incidentally. Okay? So far, so good? Yep, beg your pardon?
There must be an invariant that you expect dx to satisfy?
There is an invariant, yes. And there the invariant is at the top. If E has type T, then this is the invariant here, the typing invariant that this thing is supposed to satisfy.
I don't see a dx in that line.
There isn't a dx in that line. That's true. So, so here, if x has type, in this line here, if this x has type s, right, then this dx is going to have type s arrow s. But in a let here, down here, this one, if x has type t, then this dx will have type s arrow t. Remember the invariant here? Because the right-hand side has type t, and I'm doing grad s throughout, okay? Did that help? Beg your pardon?
Just knowing its type isn't an invariant. But why don't you go?
Okay, I'm just telling you its type of every sub-expression. Okay, so let me see. So I need to, what do I need to do? I need to take some cases. So what is this? Sophia asked about this 0. Well, so now I'm obliged, remembering this type invariant here, I need to cough up a linear map of type S arrow t, and 0 is a good, we're going to have a linear map. So I said every time we introduce a linear map, I'm going to give it semantics, but I'm allowed to cough up new linear maps. I just think of them as new constructors in the abstract data type for linear maps. Here is one, it has type for all S and T, S arrow t. And here is its semantics, right? I give it semantics just by saying what function, apply to anything, it gives me 0 in T, of course, okay? And there is a 0 in T because T is a vector space. Right? So I can come up with a 0 out of thin air. For pairs, I have something similar, but again, I need a new linear map. So the pairing rule is I'm going to just apply this differentiating operator to the two components. That gives me 2 linear maps. Now I need to take the 2 linear maps and combine them into one big linear map. How do I do that? Oh, I have this cross operator. Here it is. Oh, dear. Drat. The cross operator down here. And what does it do? It takes 2 linear maps, an S to T1 and an S to T2, and squishes them into a linear map from S to the pair T1, T2. You're forced. The types are all completely forced if you want a compositional account here. Does that make sense? So here's a new linear map. What is its semantics? Well, here it is. If I have this new linear map, M1 cross M2, and I finally apply it to something, then I finally apply it to each of the components of the sum. So I finally apply M to the something and M2 to the something and pair up the result. Okay? That's the semantics. Now I have to think, there were these primitive operators. We had multiplication and we might have addition. So for each primitive operator, primitive means does not have a definition in the language, so I need to cough up the linear map that corresponds to it. How can I do that? Well, it depends. Of course, this is where I really need to say, what is the derivative of addition? Well, and it's not so hard because we remember that the derivative of x plus y with respect to x is just 1, right? The derivative of x plus y with respect to y is also 1. So I need to somehow have some 1 things floating about, and I need to be able to combine those 1s. But this is a little different because now, instead of, you see, I've got a linear map for, this is the first component, a linear map for the second component, and now I want a linear map that takes a pair, because the input to plus is a pair, and the output is whatever it is. So I need a different kind of operator. It's sort of dual to cross. I'm writing it bow tie here. If you look at the 2 types here, where was cross? There's cross. Look at its type. It takes an S to T1, S to T2, S to pair T1, T2, and bow tie clearly goes the other way round, right? The T1 and the T2 on the left of the arrow, and the pairs on the left. So they're very, they're just dual to each other. Okay, so, and 1 behaves exactly as you might expect, and so I'm going to sort of now begin to go a bit faster and take it on trust that we can just, crank the handle here, and we can check the semantics of it. And for multiplication, we need 1 more operator, in this case scaling. Here when I differentiate x times y with respect to x, what is the derivative of x times y with respect to x? Y, very good. And the derivative of x times y with respect to y is x, right? So somehow, with plus there were 1s, now there's x's and y's. So now I actually need these, now I need, here for plus, you notice where was my definition of plus? Here for plus, I didn't use the x and y over here. I didn't need to know at what point I was differentiating, but for multiplication, I surely do. So for multiplication, the linear map for if I multiply x and y, I get this linear map here that uses x and y on the right-hand side now. Okay, so I hope you're just beginning to get the general idea. The pattern always is we need to introduce new linear map constructors in the abstract data type, and then we need to say their semantics, and then we have a little vocabulary of them. Here they all are. So there aren't that many of them. I haven't introduced vcat v and hcat v, but the others I think I've introduced. They all have nice civilized types. And moreover, they have, we can write down their semantics in a nice civilized way, and they have lots of nice properties as well as, these are, now in this slide, both the left-hand side and the right-hand side are linear maps. They have nice algebraic properties, so I'm not going to go through them. I'm just encouraging you to believe that, these linear maps are a very nice little world that has a good algebra, and we can maybe use that algebra to optimize our programs. That would be nice. Okay, so 15 minutes ago, and we're going to do, just do the last part, which is to say, let's actually do it. How do we do this? How do we now we've got as far in our plan as the full Jacobian, remember, code to build the linear map, but in the end we probably don't really want to build that linear map, we just want to know the result of applying it. And the result of applying it is what f prime and f prime r do, right? And that's going to, so we're going to, let's just see how we could do that. So let's just try to do it literally. Suppose we just we said f prime of x and dx, here it is, and suppose we took all the source code that we've just computed for df and substituted it in here, but now it's funny applied to dx, and then just optimized. When I say optimized, what do I mean? Well, we've got these rules, these properties of funny apply. That's the semantics of funny apply. So what happens if we try it? So here it is. So here's my original function, f of x is x times x. Here's the df, remember, that we just went through. And now I'm not going to drag you through all of this. I just want to show you that this first line is just, I've reproduced exactly the definition up here, right, down here. And then all I've done here is I've replaced this dfx with its definition, right? That part is just this definition here. I've replaced the dx's by the ones, because that let was pretty simple. And then all I've done in each subsequent line, I've just blindly calculated. You know, let's take this very first one. I've got something composed with something, funny applied to dx. Oh, something composed with something, funny applied to dx is something, funny applied to something, funny applied to dx. And I've just written all that out here, right? Just blindly crank the handle, as Richard Byrd would say, calculamus, right? Let us calculate. And miraculously, out of the bottom, pops the answer that we all know is, in fact, the derivative of x times x. Right? As if by magic, but just by routine program calculation. Okay? So that's the forward derivative. What about the reverse one? Well, here we just want to do the same thing, but with funny apply r instead of funny apply. We're just going to do exactly the same thing. How can we do funny apply in reverse for this? Well, again, funny apply reverse also has a similar collection of algebraic laws. These ones, remember, now are sort of derived rather than as a matter of definition. You can use these as the definition, but they're algebraic laws about funny apply in reverse, and you just crank the handle. I've put rather fewer lines in here, and I shan't drag you through it, but look at the bottom here. I get this if I stick in a, have I got this right? Should these have been paired? I'm not quite sure that I got this completely right, but what I am sure is that if you just crank the handle, it drops out in the right way. That is to say, you don't have to imply any intelligence at this point. You just have to take the code for df and apply the rules for funny apply, and you get some code which will be the reverse mode derivative. Okay? So the main thing I'm trying to encourage you to believe is that by thinking of linear maps and their algebra, you can get a sort of simple and brain-dead way to do automatic differentiation without having to think about tapes and mutation and clever stuff. Right? You just do simple stuff that even computers can do, and people can do too. Okay. All right. So let me just finish up by saying what happens when you try to do this a bit more for real. Well. One thing you might want to do is, I've really only shown you about pairs and scalars so far. You definitely want to be able to deal with vectors or matrices. And so the first thing you might want to do is to have we need to augment our language with ways to construct vectors and matrices and to take them apart. So we might want a function to construct a vector. This one here takes an ordinary, a real honest-to-goodness function from natural numbers, that's the index, to a value, and gives you a vector. So this is the standard, one standard way to specify a vector is by giving a function that gives the value of that vector at every index. Okay? I'll call it build. Then we have to think of, and that's incidentally where the lambda comes from, because you've got to say build and you've got to supply a function. So the only place in this little language I'm going to let you have a lambda is as an argument to build. I'd like to generalize this, but baby steps. So now if I'm going to differentiate build of a lambda, what's that? Oh man, well it's going to, somehow I know I'm going to have to differentiate E, right? So I'm going to think about what this function is. What is this function? Lambda I and then the derivative of E. What is that? That's a function that takes an index and gives me a linear map. So if I said build of that, this guy here, this build, that is what? What type is this thing here? The bit inside the V. What type is that? It's a vector of? There's only one answer. It's like at Sunday school, the answer is always, somebody asks a question, the answer is always Jesus. In this talk, the answer is always linear maps, right? So this guy is a vector of this build here. Since remember, this lambda produces a linear map, that grad thing, that thing is a linear map. So this is a vector of linear maps. Remember, we're just thinking of linear maps as values, perfectly first-class values. So we've got a vector of linear maps. So what does V do? V takes a vector of linear maps and produces a linear map that coughs up a vector. That's very like what we did with pairs, do you remember? It's just the n-ary version of that cross operator. It's just the vector, the n-ary version of the cross operator. And then we have to say what its semantics are. And we can write down its semantics. And then we do the same for the indexing operation to get, and everything works out smoothly. You can just add vectors in this way. And you can add other types in this way. Recursion, which, you need to write loops in this language. Certainly we're programming, we want to write loops. Mathematicians don't, but programmers do. And so we can, and in a functional world, we'd write recursion, we'd write loops using recursion. And recursion seems to work out pretty straightforwardly here. I'm sure there are depths that we haven't plumbed here, but the sort of first stab works. The thing that is really tricky, though, is sharing. So, and this shows up in at least two different ways. Number one, in this chain rule, none of you hauled me up on this, but I hope that some of you are thinking, Simon, this is a bit naughty because, look, there's this, you're calling, in calling DH here, you're going to do some work, right? But we're also calling H here. But we know that the derivative of a function is probably going to do some of the work of the function itself, right? So there's going to be some sort of work duplication. Even though you might worry about code duplication, there's going to be work duplication between calling this and calling this. So there's a little worry there, and you can maybe handle that with tupling, things like the standard tupling transformation. But the second way you need to worry about sharing is to do with let expressions. Now, when you have a let expression, you get let x equals something, and then you use x a lot of times. For forward mode, that seems to work fine, but when you do it in reverse, you've got to add up all the contributions, and somehow the fact that the invisibility of all those uses and their connection back to the starting point makes it hard to do an efficient job. The danger is you'll get something, the reverse mode thing that I described to you, if you have a lot of lets, it will work correctly, but it will not work efficiently. Right? Efficiency is the name of the game here, particularly if you're up against Tapenad and other really scarily clever pieces of software like that. So we have to be efficient. And so the question is, how can we take a principled approach to this dealing with sharing? And this is where the main payload of Conal's paper comes in, because his story is, don't compile this point-full language with explicitly named variables. Instead, translate your program first to a point-free notation in which there are no variables at all. There's just a lot of composition of functions, a lot of packing and unpacking of tuples, perhaps, right? He calls it categorical notation. He had a whole paper the previous year at ICFP called Compiling to Categories, in which he describes about how to compile functional programs to category theory. But another way to say it is compile functional programs to a completely point-free notation and then optimize that. And it does seem that compiling to this, translating to this point-free notation gives you a handle on this sharing that will let us do all the efficient things. So I'm still plumbing the depths of that, but I think I now understand why Conal was right. And that's the main game of the game with Conal, is to discover why he was right. Okay. So also good, but I would just, for me, this is the really tricky bit about reverse mode AD. It's easy to think you're fine, and then realize you've not dealt with this. It's harder than I thought, and that's where the deep stuff of Conal comes in. Okay, so we have a little proof of concept compiler. It's absolutely not production quality, but it's a little exploration tool. But it's very simple. The nice thing is that when I said AD in one slide, do you remember that? AD happens in like 15 lines of Haskell. It's the whole thing. So it's really nice, but it really does. It's not that I've told you something simple, and actually it really is as simple as that. Trouble is we've got to kind of make it as efficient as that. But it's not just a toy. It can deal with programs like this. Now, when I said the programs that machine learning people care about are fairly small, here is one that is that they do care about. It's called Gaussian mixture models. I haven't the faintest idea what it does, but notice that it's got it's building some vectors. It's got some exponentiation. It's got lots of indexing. What else is going on? There's some loops here, some sums over those vectors. It's got multiple functions that call each other. So it uses most of the things we've been talking about. It's not something that you would want to differentiate by hand, put it that way. Okay, and so we can actually,
With these if statements, you could
yes.
raise a discontinuous statement.
Oh, ifs, yes. So remember the machine learning. So imagine that you're not close to the discontinuity in the if, right? Then these machine learning things, what are you doing? You're just taking a little slope and you're going in that direction, right? And now maybe you're the other side of the discontinuity. Right, so, but remember, because you're taking little steps, remember that alpha is quite small, you're just taking a little step in that direction. So you're moving around. Now, if you give it a function that's wildly discontinuous, right, then you're going to move around in a very funny way and you're probably not going to converge. But it just seems in practice that, they do have functions that go, there's a particular important one called rectified linear unit that is, for numbers bigger than 0, it simply outputs its input. For numbers smaller than 0, it outputs 0. So at the origin, it goes, which way around is this? Is that the right way around for you? No, that's the wrong way around for you. It goes like this, right? And at the origin, it's got a little corner. But hey,
if you give, with your approach, if you give it a program that describes a function that isn't differentiable
anywhere at all.
No, sorry, that isn't differentiable everywhere.
Everywhere, yeah, that's right. Like ReLU, yes.
Yeah, so what is your approach?
Well, so what's going to happen? We're going to execute something that says, if x equals 0, then do something. Well, either it is or it isn't. Yeah. Right? And so, the program at that moment will make a decision. It'll either output this gradient or that gradient. It won't go bonkers, right? And so it will make a choice, and then you move your weights a little bit by a little delta, right? But not far. And, it might be this way and it might be this way, but who knows? And then, remember, you're doing this for 100 million dimensions, so it's only, you're not going to be on the point February. And then you'll be somewhere else, maybe not close to that anymore. So this is what I mean by it seems to work in practice. So these guys, they just don't worry about the little discontinuity. If you're Gordon Plotkin and you're writing papers about AD, then you do seriously get into domain theory, and he has a very nice paper about that. But machine learning people, they don't care. They just go and do it. So, okay. So let's see. But the real point I want to make here is just that there can be a very big difference here. The best auto-diff tools for a program like this, people will differentiate this program by hand and write C++ code by hand that is the derivative of this, right? So they will hand differentiate it and write C++. The best automatic tools produce code that runs, a factor of 10 slower than the hand-crafted, hand-differentiate, hand-optimized C++. But typical tools, quite a lot of tools, go 100 times slower, and some go 10,000 times slower. There really is a very big spectrum in how good or bad your auto-diff and optimization tools can be for this stuff. So it's quite a big payoff in doing reasonably well. And moreover, which tool is best can actually vary with the problem size quite a bit. And by the way, we are in the kind of, the 10x camp. But we're at a very early stage so far. So this is really, I had to finish here, just to say this is somewhat in the nature of paddling around the shallows, but I hope that it will have given you a slightly alternative view about automatic differentiation based on the idea of linear maps as an abstract data type that can be represented in a variety of ways. As executable code, as matrices, or, and I'm not going to spend any time on this, or indeed as syntax trees built with the constructors. This is actually a viable representation that we're using as well. And that wiggle room of having lots of representations of linear maps gives you, it helps in thinking about it and it helps in implementing it. That's it. Is there any other questions? How are we doing? Oh, 6:03, right. Yeah, okay, good.
Okay, please, do we have some questions for Simon? Sophia.
So it seems that the hand translation is better than even your tool.
So it seems that what is better than what?
If you translate these programs by hand, you get better performance than even with your tool. So my question is, rather than do it automatically, wouldn't it be better to have a refactoring tool where, I don't know, you prove some theorems and you know that the translation was correct and still fast?
Well, maybe. So you say if people can do better than computers at the moment, maybe we should just get people to do it and give them a bit of mechanical support. So
and
you could
give
say
them
that
lots
about
of
compilers
support,
in general.
yes.
I mean, you could say people can write very fast assembly code, so we shouldn't have C compilers. We should just help people to write better assembly. Maybe that's true, but I aspire to an automatic system that will jolly well, you know, go as fast as that and compile C++.
Okay, more questions, please?
A really baby question. In the example with vectors or some other data types, if you would have, how do we know that the semantics is correct?
How do we know the semantics of what is correct?
Like the example with the build and the vector. So you showed the semantics with finally apply. How do we know that that's the right semantics?
Oh, yes. So every time you give the... so if I'm going to say, this is the definition of... you know, so I've defined the semantics of V, right? But now I think you're saying, how do I know that this grad thing, that transformation, is actually producing the derivative of what would be a vector? Yeah. So that's a good question. You have to, you have to think about what is taking a derivative for vectors. So I don't have a formal proof of that at all. Maybe that would be a good challenge. I should probably think about how to prove that formally. Because you might say the same about plus, in a way. When I gave the linear map for plus, where was it? You know, it was way back here. How did I sort of asserted, you know, these things, right? I said that's the right linear map. But I didn't really prove it because it's sort of like fundamentally part of what plus is. You know, that's a sort of deep mathematical sense. You know, what does plus do and how can I differentiate it? It's the same with what does build do. Yeah. So.
Okay, do we have some more questions?
Yeah, Lemire.
So, to be the MX camp, what kind of other sorts of optimizations are you doing? And what is your runtime system? Is it in C or C++, or it is in Haskell?
Oh no! So in our little prototype compiler, we've got a little language that is really just this. It's not Haskell. It's not even Haskell core. It's completely new, completely separate, standalone language with a, and this little transforms. And it's a very small language. I showed it to you. So it's a tiny little language. It is statically typed. And the automatic differentiator just works over that language, and then there's a little optimizer for it, which we're handwritten at the moment. Maybe we can automate the construct. We'll learn somehow to do better job of optimization, and then we go from that via destination parsing style, something which you know a bit about, to C++. So we go. So the advantage of this language is so small that we can generate good C++ from it without allocating by using DPS.
Question for me, if I may. So I think it's fantastic that you've understood this stuff and brought it to programming languages audience and explained it to us. It's very clear and lucid. And I was wondering, have you gone back the other way and showed this way of thinking about things to people from machine learning? And if so, what do they make of it?
So it's really the people who are into automatic differentiation. I mean, the people who are in machine learning, they don't really care about this. They just want it to work.
I see.
Right.
Okay.
And work fast. The AD community, I think, is, at the moment, I'm just figuring out what they're doing, so I don't think I have anything new to tell them, at least not beyond what Conal has, except in this tutorial way. But maybe we'll learn something. I do think that, in general, the approach that Conal has sort of blazed the trail on, and I'm following along in his footsteps, is to say, if you take a principled PL approach to this rather wild and wacky and creative field of automatic differentiation, maybe you'll learn something new, and ultimately, perhaps we will get a kind of alchemy that will improve on the state of the art. But I think we're not at that stage yet. We haven't improved the state of the art. We're just trying to figure out how to understand it.
And a nice thing about your approach is it could work for matrices of vectors, of matrices of pairs, of whatever, because you're very general. That seems really kind of nice and appealing for its own sake, but is there a call for that in practice? Are there hacky tools that somehow auto-differentiate things somehow, but you can do it more principled. And
oh, well, yes, I mean, you really do want to. I think in an earlier slide I said, machine vision things, really you do want to differentiate something that's like a pair of, an n by n matrix and a 4 by 3 matrix. Those two. I mean, they're just two different matrices. They're not the same size. You can't even concatenate them horizontally or vertically. It's just a pair of matrices. And you really do want to take the derivative of the function with respect to both of those. And that's really difficult to do if you're stuck in an r to the m to the r to the... So the generality really is useful, I think, yes.
Cool. Okay, can we have one more question for Simon?
Yep.
Let's make it a controversial one.
It's the only thing standing between you and the pub, so...
Okay, well, in that case, let's thank him again for a wonderful final keynote.
Thanks.
Thank you very much.